Atomic structure. At its most fundamental level, matter is composed of atoms, which consist of an extraordinarily dense, positively charged nucleus made of protons and neutrons, which we collectively call nucleons, surrounded by a cloud of negatively charged electrons. The electrostatic attraction between the nucleus and electrons binds the atom together. Over 99.9% of an atom's mass resides in the nucleus because a single proton or neutron has a mass of approximately 1.66 times 10 to the minus 27 kilograms, or 1 atomic mass unit, symbolized by U, whereas an electron's mass is a mere 9.11 times 10 to the minus 31 kilograms. The scale of the atom is one of stark contrasts. While a typical atomic radius is about 1 times 10 to the minus 10 meters, that's a 10 billionth of a meter, the nuclear radius is only about 1 times 10 to the minus 14 meters, roughly 1/10,000th of the size, comparable to a pea in the middle of a stadium. Consequently, an atom is overwhelmingly empty space, a fact famously demonstrated by Rutherford's alpha scattering experiment, in which most alpha particles, which are helium nuclei, passed through a thin gold foil undisturbed when they were fired at it, but a very few were deflected dramatically, revealing that the nucleus was concentrated in the center. A specific nuclide is denoted by X with an A at the top and a Z at the bottom, but that's in front of the uppercase X. Z is the atomic number and equals the number of protons, and in a neutral atom, also the number of electrons, whereas A is the mass number, and it's the sum of protons and neutrons, the protons and neutrons added together. For example, consider carbon-12. Carbon-12 appears as stable, whereas carbon-14 is radioactive. Nuclides with the same atomic number but different neutron counts are called isotopes. Since an element's chemical behavior is governed by its electron arrangement, isotopes are chemically similar but can have vastly different physical and nuclear properties. Carbon-12 is stable, while carbon-14 is used in radiocarbon dating because it's radioactive. Similarly, uranium-235 is fissile and powers nuclear reactors and weapons, unlike other uranium isotopes. Electrons occupy specific quantized energy levels, or shells, whose capacities in simple models follow the sequence 2, then 8, then 8, and so on, meaning 2 electrons occupy the first shell, 8 the second, and 8 the third. An electron can absorb a photon of a precise energy to jump to a higher level, and it emits a photon of that same energy when falling back to a lower level. This process produces the characteristic spectral lines of elements, such as hydrogen's visible Balmer series, which includes the H-alpha line at 656 nanometers. Supplying energy equal to or greater than the ionization energy removes an electron entirely, which creates an ion. This principle of ionization underpins electrical conduction in metals, the formation of ionic bonds, and the operation of devices like fluorescent tubes, where excited electrons emit photons to produce lights. I would just like to say something about the formation of ionic bonds. an example, if you will. Sodium, symbolized by Na, with an atomic number Z equal to 11, has an electron configuration of 2, 8, 1. That means 2 electrons in the first shell, 8 in the second shell, and 1 in the third outermost shell, or the valence shell. And it loses an electron in the third outermost shell to become Na+, which is a positive ion. While chlorine, symbolized by Cl, with an atomic number Z equal to 17, has an electron configuration of 2, then 8, then 7, which adds up to 17. This gains 1 electron to become Cl-. Na plus and Cl minus ionically bond together and in fact form an ionic lattice together overall. These foundational atomic concepts, the distribution of mass and size, nuclear notation and isotopic variation, and the quantized behavior of electrons, directly enable key techniques and phenomena. Mass spectrometry separates and identifies isotopes. Radiometric dating relies on isotopes like carbon-14. Nuclear fission applications depend on specific nuclides like uranium-235, and chemical bonding is predicted by electron configurations, and elements are identified through their unique line spectra. Now let's talk about states of matter and particle motion. Matter, especially in our everyday experience, exists in 3 principal states: solid, liquid, and gas. A manifestation of the competition between the thermal kinetic energy of particles and the electrostatic intermolecular forces binding them together. In a solid, particles are locked in a dense, regular lattice, vibrating about fixed positions. This structure grants solids a definite shape and volume and enables thermal conduction through these vibrational waves. In liquids, particles remain densely packed and in close contact, but lack long-range order, allowing them to slide past one another. This fluidity is exploited, for example, in systems like hydraulic brakes. Finally, in gases, particles move at high, random velocities. Did you know that air molecules, for example, have an average speed of around 500 meters per second at room temperature? Even when the air seems motionless and still, that's how fast they're moving, on average. Gas particles have large separations, which make the interparticle forces more or less negligible. This results in low density for the gas, roughly 1/1000th that of solids or liquids, and high compressibility, which is used in pneumatic tools and gas canisters, and the exertion of pressure via collisions with container walls, the fundamental process powering steam turbines and internal combustion engines. Density is the amount of mass per unit of volume. We symbolize density with the Greek letter rho, which kind of looks like the letter P. Therefore, the formula would be rho equals m over v. M divided by v, mass divided by volume. It's determined by particle mass and packing efficiency, and it generally follows the order that the density of a solid is greater than the density of a liquid, which is much greater than the density of a gas. That's the general order of things, and that correlates with our day-to-day experience. But a critical exception is water. Due to its open hexagonal hydrogen bonded lattice, ice is actually less dense than liquid water, which allows it to float, and that insulates aquatic ecosystems. Matter can actually not only exists in those different states, but it can change state. There's melting or freezing, depending on which way you're going, from a solid to a liquid. And there's boiling or condensing, which is from a liquid to a gas. Those are physical, reversible processes where mass is conserved because the particle count remains constant. You have the same number of particles before as after, therefore mass is conserved. The energy supplied during these transitions, known as latent heat, overcomes the attractive forces and increasing the system's internal potential energy without raising its temperature. This appears as distinctive plateaus on heating or cooling curves. Sublimation, you may have heard of, when a solid becomes a gas directly, bypasses the liquid phase entirely. An example of this is solid carbon dioxide, known as dry ice, which sublimes at -78.5 degrees Celsius. And here on Earth we use that for cooling applications and special effects because it looks quite cool when that happens. It's particularly relevant on the planet Mars. The kinetic particle model underpins the explanation of key phenomena. It accounts for Brownian motion, which is the erratic jittering of smoke or pollen grains, which provides direct evidence of invisible molecular bombardment, and evaporation, a surface cooling process in which the most energetic particles escape a liquid below its boiling point, exemplified by perspiration. Let's say something else about density. Density, remember, is symbolized by the Greek letter rho, which looks like a P, but it's not the same as the letter P. It's an intrinsic material property defined as the mass per unit volume. And so, remember, rho is equal to mass divided by volume. Its standard unit is kilograms per meter cubed. What is the most dense element? That would be osmium. But you can also see grams per centimeter cubed. So 1,000 kilograms per meter cubed is the same as 1 gram per centimeter cubed. A cubic centimeter is something similar to the size of a sugar cube. And what has a density of around 1 gram per cubic centimeter? Well, that would be water. An object's density relative to a surrounding fluid determines whether it floats or sinks. In water, which, as I say, has a density of approximately 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter, Objects less dense than this will float. When it comes to a human body, well, that depends on how much air is in your lungs. Accurate density determination requires precise mass and volume measurements. Mass is typically measured using an electronic balance. Volume measurement depends on the sample's form. If you have a regular solid, like a steel cube, you can calculate volume geometrically using formulae that you know, and with the assistance of precision tools like vernier calipers or micrometers, taking care to minimize zero error. But if you have an irregular solid, like a chess piece, a volume can be found by fluid displacement. This is through applying Archimedes' principle, which is that the object is submerged in a eureka can, and the volume of water that's displaced and overflows into a measuring cylinder is equal to the object's volume. For a liquid, the mass of a known volume is measured. This involves weighing an empty measuring cylinder, adding the liquid, and then subtracting the tare mass to find the liquid's mass, and dividing by volume. Read at eye level, at the meniscus to avoid what's called parallax error. These techniques are foundational for identifying unknown substances, like in testing the purity of gold, and they're critical for engineering applications, such as calculating load-bearing limits in construction materials. Let's talk about changes of state and energy. The transfer of thermal energy to a substance alters its internal energy in two distinct ways: by raising its temperature or by changing its state. These processes are governed by two key properties: specific heat capacity, which has the symbol C, and specific latent heat, which has the symbol L. Specific heat capacity, which, as I say, has a symbol C, quantifies a substance's thermal inertia. In other words, how resistant it is to heating up. It is the energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. Let's say that again. The specific heat capacity of a substance is the energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. A high specific heat capacity means a substance can absorb significant energy with only a small temperature increase. Water has a remarkably high specific heat capacity of around 4,200 joules per kilogram degree Celsius. It's therefore ideal as a coolant in car engines and for central heating, as it stores vast thermal energy while stabilizing temperature. By contrast, copper, which water was 4,200, copper is 390 joules per kilogram degrees Celsius. That heats up but also cools down very rapidly. When a substance reaches its melting or boiling point, further energy input does not raise its temperature. If you've ever noticed the pot of boiling water on the stove does not just continuously get hotter and hotter and hotter until it's hotter than the sun or as hot as fire. That doesn't happen. Instead, by continuously adding thermal energy, it breaks the intermolecular bonds to change state. The energy per kilogram required for this phase transition is the specific latent heat, symbolized by L. And you can calculate it as E equals mL. During the change, the kinetic energy of the particles related to the temperature remains constant, while the potential energy of the whole system increases. This is categorized into the specific latent heat of fusion for melting or freezing, and the specific latent heat of vaporization for boiling or condensing. For example, let's consider water. Melting ice absorbs 334,000 joules per kilogram, which is a principle used to cool drinks. Similarly, sweating cools the body because evaporating water draws the latent heat of vaporization from the skin, and the latent heat of vaporization is over 2 million joules per kilogram. By the way, a fun fact, did you know that kangaroos lick their arms to cool down? You can actually do that if you're in trouble. You can, although it's kind of gross. In the laboratory, these values are determined using an immersion heater, where the electrical energy supplied to change the state of a known mass is measured. Okay, let's talk about gas pressure and temperature. So, gas pressure arises from the countless microscopic collisions of particles in constant random motion. Each collision with a container wall involves a change in the particle's momentum, exerting a minute force. Macroscopically, on the big scale, pressure then is the aggregate of these forces distributed over the wall's area. So that's why we define pressure as force per unit area, P equals F over A. And if you think about it, it's a direct application of Newton's second law as well because of this. The temperature of a gas corresponds directly to the average translational kinetic energy of its particles. At absolute zero, which is a very special temperature indeed, about minus 273.15 degrees Celsius, the motion is theoretically zero. It ceases altogether. although you can't actually reach that temperature in practice. Raising the temperature increases this average energy, causing particles to collide with the walls both more frequently and with greater individual force. Consequently, if the volume is held constant, pressure increases linearly with absolute temperature. That's a relationship that's formalized by Gay-Lussac's law. This principle explains practical dangers, such as an aerosol can exploding in a fire, or a car's tire pressure rising after sustained highway driving. Alternatively, if temperature is held constant, pressure is governed by collision frequency alone. Reducing the volume of a gas forces its particles to strike a smaller wall area more often, thereby increasing the pressure. This inverse relationship, where pressure multiplied by volume is constant, is called Boyle's law. And it's often remembered as PV equals C, or PV equals K. The point is, pressure times volume equals a constant. And that's exploited in devices like bicycle pumps and syringes, where compressing a volume creates the high pressure needed to move air or fluid. These empirical laws, the linear proportionality of pressure to absolute temperature at constant volume and to the inverse of volume at constant temperature, serve as direct experimental validation of the kinetic theory of gases, which successfully links macroscopic, that's big scale properties, to the statistical behavior of microscopic particles. Okay, let's now move on to talking about forces and motion. So let's begin by talking about scalars and vectors, and like what are these and how are they different, or how are they related. So physical quantities are fundamentally divided into two categories: scalars and quantities. Scalars are defined solely by magnitude. For example, distance, or speed, or mass, or energy, or time. Whereas vectors possess both magnitude and direction. So the vector version of distance would be displacement, and the vector version of speed would be velocity. There's also acceleration and force, weight and momentum. This distinction is needed. It's very essential because vectors must be treated geometrically, not just through ordinary arithmetic. So you might say through vector arithmetic. The difference is clearly illustrated by the concepts of distance and displacement. Distance is the total scalar length of a path traveled, while displacement is the net vector change in position from start to finish. If I take 2 steps to my left and then 2 steps right, the distance traveled is 4 steps, the displacement is 0. 0 steps. So, another example is that a runner completing a 400-meter lap of a circuit covers a distance of 400 meters but achieves zero net displacement. Also, a satellite orbiting at a constant speed nonetheless experiences continuous acceleration. And why is this the case? Because acceleration is defined in terms of velocity, which is it's the average rate of change of velocity or the instantaneous rate of change of velocity, and that's a vector. And that velocity vector is constantly changing direction. And it's a change sustained by a centripetal force. Vectors can be represented graphically by arrows whose lengths are proportional to the magnitude that you intend to convey, and they are combined with each other using the tip to tail method. Right, so imagine one arrow connected to the other from the tip to the tail. For instance, imagine if you have two orthogonal forces. That means perpendicular at right angles to each other. And one is 3 newtons and the other is 4 newtons. This will yield a resultant force of 5 newtons. Just use the Pythagorean theorem. And its direction is given by trigonometry, simple right-angled trigonometry. Now, conversely, equal forces acting in opposite directions can cancel each other out to produce equilibrium. This inherent directionality is critical for analyzing motion and forces. It distinguishes mass, which is a constant scalar, from weight, which is a gravity-dependent vector given by weight equals mass times gravity. If I were teleported to the moon instantaneously right now, my mass would be the same, but my weight would be different. It would be less. And it allows for subtraction of vectors to find relative velocities, such as a headwind reducing an aircraft's ground speed. Also, it enables the resolution of a single vector into perpendicular components that are going at right angles to each other. This is a technique used to split a projectile's velocity into independent, horizontal, and vertical parts. Or you could calculate the component of weight that's pulling an object down a ramp, for example. That's another example. So now let's talk about distance, displacement, and speed and velocity. Although I kind of covered these a little bit before. Motion is fundamentally described by scalars and vectors, as I say. Distance measures the total scalar length of a path traveled, while displacement is the vector representing the straight line change in position from start to finish, and it possesses both magnitude and direction. Similarly, speed is the scalar rate of covering distance, and velocity is its vector counterpart, where you specify speed and direction. So what is the governing equation for speed? Well, it's that, or rather for velocity, it's that velocity is the change in displacement over the change in time. Whereas for speed, it's d over t, which is the change in distance over the change in time. And that can be applied directly to something which has constant motion. Whereas for variable motion, you need to use what are known as the Suvat equations as long as the acceleration is constant. Okay. Let's say something more about acceleration. Acceleration is the vector quantity defining the rate of change of velocity, calculated as the final velocity of the object minus the initial velocity of the object divided by the amount of time that the object has been traveling. And you measure it typically in meters per second squared, which makes sense because velocity is measured in meters per second and acceleration would be meters per second, so meters per second squared. Positive acceleration indicates that you're speeding up in the direction of motion, while negative acceleration, called deceleration, signals that you're slowing down or reversing direction. When time is unknown, you can use a time-independent equation, v squared minus u squared equals 2as, which directly links velocity change to displacement. This relationship that I just said, v squared minus u squared equals 2as, reveals a critical real-world principle, and that is that braking distance in a car, for example, is proportional to the square of speed. So doubling a car's speed from 30 miles per hour to 60 miles per hour multiplies the stopping distance, the distance you need to stop, by 4. You've doubled the speed, so now your stopping distance is multiplied by 4. Near the surface of the Earth, all objects in free fall experience a uniform gravitational acceleration, which the symbol is g, and it's approximately 9.8 meters per second squared, but you can round it to 10 meters per second squared for calculations. And this means that a dropped object, regardless of its mass, it doesn't matter if it's an iron ball this big or as big as a house, it will accelerate to roughly 30 meters per second after 3 seconds of falling. So from the instant you let it go, 0 meters per second. 1 second later, it's falling at 10 meters per second. 2 seconds later, 20 meters per second. 3 seconds later, 30 meters per second. Like that. And that demonstrates what's known as Galileo's principle. In reality, however, air resistance complicates this ideal. Fluid friction actually increases with velocity until it balances the object's weight. This is why a penny dropped from a plane won't kill you, and it won't be going at the speed of of a bullet or something like that, because things have what's known as a terminal velocity. For a human being, it's approximately 120 miles per hour. And for a cat, it can actually, if it's healthy and young, it can actually survive the falling at its terminal velocity, or landing at its terminal velocity, I should say. So at this equilibrium, the resultant force and acceleration becomes zero. That's what I mean by terminal velocity. And for a skydiver, that's typically between 50 and 60 meters per second. Okay, and what about distance time and velocity time graphs? How can we think about graphs? Well, these are trying to visually encode information, and therefore there's little that I can actually say about them here. But I will just say a few words about them. On a distant time graph, the gradient, or the slope, represents the speed. Therefore, a horizontal line would indicate a stationary object, and a straight diagonal line would show constant speed. But if you think about it, stationary speed is a constant speed. It's just a special case. Anyway, a curve might signal acceleration or deceleration. Kind of depends on the way that it's going. But the changing gradient reflects the changing speed. That's how you know. Now, for a velocity time graph, this provides richer information. Its gradient directly represents acceleration. A steeper slope means greater acceleration or deceleration, while a zero slope indicates constant velocity, which is not the same as being at rest, by the way. I need to say that. And what about the area underneath the graph between the plot line and the time axis? Well, that represents the total distance traveled, which makes sense because velocity multiplied by time equals displacement technically, but if it's a speed time graph, then it's distance. Okay. For non-uniform motion, like a car accelerating, cruising, then braking, your velocity time graph would look like a kind of a polygon, and you can calculate the area underneath the graph by dividing it into regular shapes like rectangles and triangles. So with all that said, let's talk about Newton's first law, or let's think about Newton's first law. This is the statement that an object's velocity, its speed and direction, remains constant unless acted upon by a non-zero resultant force. This principle of inertia contradicts our everyday experience in a friction-filled world, if you think about it. Because in day-to-day life, objects appear to slow down on their own. Now, a resultant force of zero defines a state of equilibrium, which manifests in two distinct ways. The first way is static equilibrium, where an object at rest experiences balanced forces. Like, think of a book on a table with the normal force, which is what's stopping it from going through the table, cancelling its weight. But there's static equilibrium like that, a book on a table, and there's also dynamic equilibrium, where an object moves at constant velocity because forces are balanced. Like a car, when a car is cruising at a steady speed, which means that the engine thrust precisely offsets the air resistance and the friction on the road. Therefore, motion itself does not require a force, but a change in motion does. For instance, a vehicle turning a corner at constant speed must have a resultant force acting on it. And that's the centripetal force from friction, and that changes its direction of motion. Now, on the other hand, a skydiver falling at terminal velocity has zero acceleration, precisely because air resistance has increased to the point where it equals their weight, resulting in a net force of zero, and thus a constant velocity as described by the first law. So that's Newton's first law. Is there a second law? Well, yes, there is. This presents the fundamental proposition of dynamics that the net vector sum of all acting forces governs a body's acceleration. You may know it as F is equal to ma, but it should really be F net equals ma. And here acceleration is directly proportional to this resultant force and inversely proportional to the inertial mass. Operationally, mass in kilograms, force in newtons, and acceleration in meters per second squared are required. For example, a 1,000 kilogram car being propelled forward by a 5,000 Newton engine force but impeded by 2,000 newtons of resistance experiences a net 3,000 newtons, and therefore applying F equals ma, this yields an acceleration of 3 meters per second squared. The Newton's second law, elucidates diverse phenomena like a laden lorry accelerates more sluggishly than an empty one under identical thrust, which is something we all intuitively know. And now we can actually say why that is. It's because increased mass diminishes acceleration for a given net force. It further explains lengthened braking distances with speed. Greater kinetic energy demands a larger decelerating force or longer displacement to halt the mass. And lastly, it dictates the ascent of a rocket. That's the last example, where constant thrust applied to a diminishing fuel mass produces rapidly escalating acceleration. Okay, so what is inertial mass though? Well, inertial mass is defined precisely as the ratio of applied force to resultant acceleration. and it quantifies an object's intrinsic resistance to changes in its state of motion. By defining it this way, we deliberately decouple the concept from gravitational interaction. A 100 kilogram anvil and a 1 kilogram pillow are both weightless in deep space, but exhibit vastly different inertia. Accelerating the anvil demands 100 times the force required for the pillow to achieve an equal acceleration, even in deep space. This fundamental property of sluggishness has direct engineering consequences, of course. For instance, in collision safety, a vehicle's high inertial mass necessitates a correspondingly large force to rapidly arrest its momentum. So, crumple zones at the front of cars are therefore employed to lengthen the collision duration, thereby diminishing the peak force exerted on the occupants of the car, the driver, for example. And that's a direct translation of inertial resistance into a structural design requirement. Okay, so I've mentioned weight earlier, W equals mg. Let's talk about weight a little bit more and gravitational field strength. Mass is an intrinsic scalar property, which you measure in kilograms and variants of that. It quantifies both the quantity of matter and an object's inertia, or its resistance to acceleration. It remains constant irrespective of location. It doesn't matter where you are, you will have the same mass if I teleport you here or there. Weight, by contrast, is an extrinsic vector force, and you measure it in newtons, and it represents the gravitational pull exerted on that mass by a celestial body like Earth or the Moon or Mars. The two are related by that linear equation I mentioned earlier, W equals mg. Weight equals mass times the gravitational field strength. And remember, the units for G are newtons per kilogram, which makes sense because weight is measured in newtons, mass is measured in kilograms, and therefore G must be measured in newtons per kilogram. That's how it can make sense. On Earth, G is approximately 9.8 newtons per kilogram. Therefore, a 1 kilogram mass experiences a weight force of about 10 newtons. I'm 75 kilograms, so I would be about 750 newtons. My weight, that's what my weight would read here where I'm standing now. But it varies with proximity to planetary mass, how close you are to the planet's mass. And the Earth is a little bit flattened at the poles, like an abacus bead. And gravity is actually ever so slightly stronger at the North and South Pole, towards there. So not only does it vary with where you are on the planet's surface, if it has a surface, but it also varies with the proximity to the planetary mass. 100 kilogram rover, for instance, possesses constant mass but exhibits location dependent weight. So it's around 1,000 newtons on Earth and 160 newtons on the Moon. because the gravitational field strength on the moon is about 1/6 that of Earth, but it's 2,600 newtons on Jupiter, because on Jupiter G is 26. This physical distinction dictates measurement methodology. Weight is measured directly using a calibrated spring, which is called a Newton meter, and that relies on the extension of a spring under load. And mass can be, or is, determined independently of gravity using a beam balance to compare against known standard masses, or a top-pan balance pre-calibrated for a specific planetary G, which is what you see on the bathroom scales. The weight force acts through a single point, which is called the center of gravity, and it's a concept critical to stability analysis. Clarifying the mass-weight dichotomy can help you resolve apparent paradoxes, like an object in deep space being weightless yet retaining its full inertial mass, requiring force to accelerate according to Newton's second law, F equals ma. Mass is essentially immutable, whereas weight is circumstantial. You can think of it that way. Okay, so I mentioned resultant forces earlier. Let's speak about that a little bit. So what is a resultant force? It's the singular vector equivalent obtained through vector summation, where direction dictates sign, which replaces all individual forces acting on an object to produce precisely the same kinematic effect. In other words, if you have 500 force vectors acting on an object, you can reduce it all down to just one, the resultant force. This is modeled in free body diagrams, or FBDs, by isolating the object as a particle, modeling it as a particle, and representing forces as arrows scaled to magnitude. For collinear forces, the resultant reduces to just a simple algebraic sum because the arrows are going in the same direction. So like a car with 5,000 newtons of forward thrust and 2,000 newtons of resistive drag experiences a 3,000 newton resultant accelerating it forward, while a skydiver at terminal velocity with weight and air resistance both being 800 newtons yields a resultant of 0 newtons. So these are really simple calculations because they're essentially just one-dimensional. Beyond linear subtraction and addition, you have the situation of orthogonal forces, such as a boat with engine thrust north and current flowing east, which requires vector resolution, often visualized qualitatively or calculated using the Pythagorean theorem from earlier, and then using simple trigonometry to get the bearing. Okay, so I mentioned two of Newton's laws, Newton's first law and Newton's second law. So what is Newton's third law? Newton's third law states that forces always arise in reciprocal pairs. If object A exerts a force on object B, then object B simultaneously exerts a force of equal magnitude and opposite direction on object A. So like in symbols, you would say FAB equals negative FBA, like that. These paired forces act on different bodies and are of the same physical type. This distinguishes them from balanced forces on a single body, a distinction that's commonly mistaken. For instance, a book resting on a table has its weight determined coming from Earth pulling the book, but that's balanced by the normal contact force, which is from the table pushing the book. But these are not a third law pair. The true partner to the book's weight is the book's gravitational pull upward on the Earth. You see, the partner to the table's upward normal force is the book's downward contact force on the table. All practical manifestations of the law rely on this reciprocal recoil. A rocket accelerates because its engine violently expels exhaust gases backward. The gas exerts an equal and opposite forward thrust on the rocket. A swimmer propels themselves forward by pushing water backward. In a collision between a small car and a truck, the forces on each vehicle are equal in magnitude, but the car's smaller mass results in a far greater, more destructive acceleration, since acceleration is force divided by mass. A equals F over m. Okay, so we've covered a lot of ground. Let's now go a little bit further, just a little bit further, and talk about momentum. What is momentum? Momentum is, well, it's kind of like oomph. It's a vector quantity, which is defined as the product of an object's mass and its velocity. So P equals mv. Wait a minute, its symbol is P? That's right, because we're already using m to stand for mass. So we need to use the another letter for momentum. Its letter is P. Okay, so what about its units? Well, it's mass times velocity, so that would be kilograms times meters per second, right? That's right, kilogram meters per second. And what is it trying to measure? It's trying to measure fundamentally how difficult it is to halt a moving object. Momentum obeys a strict conservation law within any closed system, one with no net external force. I'm saying the total momentum before an interaction must equal the total momentum after. Its vector nature is essential. Direction matters, so that velocity in one direction is assigned positive value and velocity in the opposite direction is assigned negative value. This explains phenomena like recoil. When you fire a gun, you get jolted backwards. So, think about that as a stationary system at first. At first it's stationary because you're just holding the gun, that's all. Before firing, the total momentum is 0. And upon firing, the forward momentum of the projectile, positive mv, is precisely counterbalanced by the backward momentum of the rifle, negative mv. So a consequence of this is that a lighter firearm must recoil with a higher velocity than a heavy cannon to achieve the same magnitude of opposing momentum. Collisions provide a clear demonstration of this conservation. So consider, for example, a 1,000 kilogram car, which is quite a small car, moving at 20 meters per second that rear ends an identical stationary car. If the two lock together in a perfectly inelastic collision, the initial momentum will be 20,000 kilogram meters per second, and that must be conserved. That momentum is now distributed across a combined mass of 2,000 kilograms, resulting instantly in a shared velocity of 10 meters per second. And these kind of calculations are foundational for investigating crashes and for engineering safety features like crumple zones, which is designed to manage the force produced by the change in momentum. By combining P equals mv and F equals ma, you get F equals the change in momentum over the change in time. And so the goal in that situation would be to extend the duration of that change. Okay. Now, I mentioned stopping distance earlier. It's important to say a few more words about that. Stopping distance is the total scalar displacement from when the hazard is perceived to a full stop. And it comprises two distinct phases. First is the thinking phase, the thinking distance, and second is the braking distance. Thinking distance is the linear product of the initial speed and the driver's reaction time, which typically spans between 0.2 to 0.9 seconds, but it can be extended by impairments such as intoxication, fatigue, distraction, or even drug use. Braking distance, on the other hand, arises from the work energy principle. The braking force must perform work equal to the vehicle's kinetic energy. Since kinetic energy scales with the square of speed, braking distance grows quadratically. You double the speed, that quadruples the stopping span. You triple the speed, that multiplies the stopping span by 9. This non-linear dependence is fundamental to highway safety design. The actual braking distance is further governed by the vehicle's mass and the effective coefficient of friction, which deteriorates with poor road conditions, like having ice on the road or standing water, which causes hydroplaning or mechanical wear, such as bowled tires or degraded brake pads in your car. I want to now talk a little bit about forces and elasticity. So let's start out by saying that deformation, and let's explore deformation. Okay, so deformation is the alteration of an object's dimensions through stretching, compression, or bending, and it's a process that fundamentally requires multiple opposing forces. Without such a balanced system of forces, an object would simply accelerate as a rigid body. To induce a change in shape, one must apply, for instance, equal and opposite forces at each end of a spring. Within a certain set of conditions, this deformation is elastic and reversible. The object recovers its original geometry when the forces are removed, and this behavior is modeled by what's known as Hooke's law, which states that force is directly proportional to extension, F equals K times E. K is the spring constant, which is a number specific and attached to the spring in the situation, and it's a measure of how stiff the spring is, and it's measured in newtons per meter. Graphically, this yields a straight line through the origin if you were to have force versus extension plotted on a graph. However, this linear relationship is of course bounded. It can't carry on forever because a spring can't stretch forever and extend forever. It holds only up to what's known as the limit of proportionality. Beyond this limit, or for inherently nonlinear materials like rubber, the relationship becomes curvilinear. If extended past the elastic limit, the material undergoes inelastic or plastic deformation, and it's permanently reshaped. You've changed it fundamentally. The work performed during elastic deformation is not dissipated, it is stored as elastic potential energy. Numerically, this energy is equal to the area under the force extension curve, given by half ke squared for the linear region, which makes sense if you think about it. This principle of energy storage and controlled release is harnessed practically in systems ranging from vehicle suspensions to the driving mechanisms of clocks. Okay, and the last sort of thing that I want to talk about now is circular motion. So there's linear motion, which is in a line, and there's also circular motion around a circle, and there's also harmonic motion, which is like back and forth. But let's just talk about circular motion right now. Uniform circular motion presents an apparent paradox. An object moving at constant speed around a circle, nevertheless, is continuously accelerating. How do you explain this? Well, this occurs because velocity is a vector defined by both speed and direction, and its speed isn't changing, it's that its direction is constantly changing. So a changing direction alone constitutes acceleration. The resulting centripetal acceleration is invariably directed radially inward toward the center of rotation. It is produced by a net centripetal force, which is always perpendicular to the object's instantaneous velocity. Since this orthogonal force does no work, the object's kinetic energy, and thus its speed, remains constant. Now, critically, centripetal force is not a distinct type of force, but a descriptive role played by whatever net force maintains the circular path. Context determines the physical origin. gravity for a satellite's orbit, tension for a world hammer, a hammer that you're whirling around, and friction for a car rounding a bend, or electrostatic attraction for an electron bound to a nucleus. In each and every single case, this inward directed force counteracts the object's innate tendency, per Newton's first law, to travel in a straight line tangent to the circle. The motion, therefore, is a dynamic equilibrium between inertia and a constantly redirecting central force.